there. So in the previous parts of the videos, we've talked about like complex variables and how to interpret them on the complex plane. And then we discussed the basic algebraic operations of addition and multiplication and what these mean geometrically. Now there's also a very important idea known as taking the conjugate of a complex variable, and let's see what that is, and then we'll again talk about the product of two complex variables and see how that relates to our sort of how it relates to the other concepts that we know in terms of taking products of two vectors, in particular scalar product and vector product. So let's just talk about what the complex conjugate of a variable is. So given a complex variable z, let's say x plus iy, its conjugate is defined as z bar, and it's obtained by, so if y is the imaginary part of the complex variable, we change the sign of the imaginary part from plus to minus or minus to plus. So in particular, in this case, the complex conjugate is x minus, defined as x minus of iy. And this is sometimes also denoted as, there's other ways of denoting, so we can write this as z bar, and some people also write it as z star. Now, so again, it's basically flipping the sign of the imaginary part. So if it was plus, we flip it to minus, and we can again take the conjugate of this. So maybe we can write z bar bar, taking the conjugate of this, and then we'll again flip the sign of the imaginary part, and then we'll get x plus iy. So we get back z. So if we take the conjugate twice, we get back the original variable z. Now this also has a geometric meaning, which is if our complex variable z in the complex plane is, let's say it's here, and we draw the vector like this. So this is z, which is x plus iy, and this is our real axis, and that's the imaginary axis. Then taking the conjugate means reflecting this variable off the x-axis, because what we are doing is we are flipping the sign of the imaginary part. So if the imaginary part is positive here and we flip the sign, then we'll get the variable z bar here. So z bar is here. So this is like a reflection of the imaginary axis. So we're reflecting this and seeing its image of the imaginary axis. So this can be thought of as reflection of the real axis, reflection of the real axis. And hence we can see if we take the conjugate twice, then we are reflecting z bar off the real axis again, and then we end up coming back to z. So that's like taking two images. So it's like a reflection, and that's why, so that's more of a geometric meaning for what the conjugate stands for. Okay. Now, so in the previous video, and I'll put a link, we talked about the product of two complex variables as something that gives us the product of the modulus of the two complex variables, and the argument is the sum of the two arguments. And in terms of thinking of the complex product as an operation being performed by one variable on the other, we can think of this as an amplification and a rotation. But it'll be useful, like since we are thinking of complex variables in the complex plane as vectors, what does this product mean in terms of the product of two vectors that we're more familiar with? So again, let's think about z1. Let's talk about one complex variable z1, which is x1 plus iy1, and then we think of z2 as x2 plus iy2. Now if we take their actually, let's also define two vectors, which is r1, which we can think of x1 in the x direction plus y1 in the y direction. And then, so corresponding to this complex variable z, we're defining a vector r1. And then we can define another vector r2 corresponding to this complex variable x2 ex plus y2 ey. Okay. So let's first see what is the scalar product of these two vectors and the vector product of these two vectors. So let's talk about the scalar product. Scalar product is r1 dot r2, right? And so what this means for these two vectors is that when we dot r1 with r2, the dot product, since Ex and Ey are sort of linearly independent and orthogonal vectors, the dot product of Ex and Ey will be 0. So the only components that remains will be x1, x2 plus y1, y2. So that's the scalar product of these two vectors. So let's keep this in mind. Okay, and then what about the vector product or the cross product? So since this is since we're in the two-dimensional plane, we know that the cross product would only have one component, which is so let's write the cross product as R1 cross R2, and the way to calculate it in the standard way is we can think of defining this sort of matrix with components Ex, Ey, Ez, which is the three directions, and then we have the components of the first vector, which is it's x1 along here, x2 here, and 0 here, and the second vector, y1 here, and the second vector is x2, y2, 0. And this cross product will then only have one component, which will be the Ez component, and that will be x1, y2 minus x2, y1. So x1, y2 minus x2, y1 along the z direction. Because the other components have a 0, so if we try and calculate the component along Ex, we find that it will be 0 because this product is 0 and this is 0. Similarly, Ey will be 0. So we just have one component. Okay, so let's keep these two things in mind, and let me write it here for convenience. So the dot product is x1, x2 plus y1, y2, and the cross product is x1, y2 minus x2, y1. Okay. And now let's revisit the way we defined the product of two complex variables. Now, if we take z1 times z2, then we see, let's just do it again, it's x1, x2, and then minus y1, y2 plus I times x1, y2 plus x2, y1. Now, if we try and compare it with the scalar product and the vector product that we have for the vectors corresponding to these complex variables, then we see that there is a sign problem, in the sense that if we want to give a meaning to this in terms of these quantities, there is a sign problem. There is a minus here and there's a plus in the scalar product, and in the vector product we have an x1, y2 minus x2, y1, and here we have x1, y2 plus x2, y1. So it seems that they are somewhat related, but there is a problem, there is a difference in the signs that we are picking up. So so one of the things we can do is think about taking z1, the product of z1 with z2 conjugate, which is what we just defined. So z2 conjugate is x2 minus I times y2. And then let's see what the product z of z1 with z2 conjugate looks like. So if we multiply these two, then we have x1, x2 as the first term, x1, x2. Then we have minus of I, y1, y2, minus of I square, y1, y2. Now minus of I square will give us a plus, so we have plus y1, y2, okay, and then we have an I. Then we have x2, y1 positive, and then we have minus x1, y2. Right. So now you see that if we compare this with the scalar product, we find that the first term, the real part of the complex product, is actually the scalar product of the vectors associated with z1 and z2. So we have x1, x2 plus y1, y2, and that's the scalar product. And this term, which is x2, y1 minus x1, y2, is actually minus of the vector product of these two quantities, x1, y2 minus x2, y1, and that's the vector product. Minus of the vector product. And in fact, if we take the conjugate of this, which is, had we defined this as z1 bar z2, we find that if we take the conjugate of this quantity, then we find that we'll get the same scalar product, but exactly the vector product, because we'll pick up a minus sign here. So in fact, if I take the conjugate of this, z of bar, z of this, the conjugate of this variable, then we'll find this is x1, x2 plus y1, y2. The real part remains the same, minus of this, which will give us plus I times x1, y2 minus x2, y1, which is z1 bar z2. And so this is again the positive vector product, and this is the scalar product. So this is an interesting idea, that the product of two complex variables, or rather if we take the product of a complex variable with the conjugate of the other variable, it encapsulates both the notions of the scalar product and the vector product of vectors, two-dimensional vectors that we're familiar with. So this was one of the ideas that I thought is interesting to discuss. Another thing that comes up here is that again, going back just a little bit to the discussion of when we define the conjugate of two complex variables, if we have a product of two complex variables z1, z2, then the conjugate of the product of this quantity is actually the conjugate of each of them independently. And this is an interesting exercise that one can check. If we have product of multiple complex variables, their conjugate is nothing but the product of the conjugate of the product is nothing but the product of the conjugates. This is something I just used quickly to go from z to z bar. But it's a good thing to check for once. So let's continue in the next parts and discuss more ideas associated with complex variables. See you there. Thanks.